Hey, this is Sanyam Bhutani, and you're listening to Chai Time Data Science, a podcast for data science enthusiasts where I interview practitioners, researchers, and Kagglers about their journey, experience, and talk all things about data science.
Welcome to Quarantine Chai with Machine Learning Heroes, the CTDS.Show. In this episode, I interview the VP of Applied Research at Nvidia, Bryan Catanzaro. We, as you might expect, talk all about Bryan's journey into machine learning and deep learning and his journey at Nvidia as a proxy to also understanding how the field has shaped itself over the years. We start by talking about Bryan's journey into parallel computing and optimizations. How did he get started in these problems leading up to the CuDNN framework, which Bryan has co-authored? We also dive into his research groups and his research work at Nvidia. Bryan is leading different groups of research teams, and we dive into what does research at Nvidia really look like. Towards the end, we also talk a little about the RTX 3000 series and the really exciting 3090 GPU, which I'm personally really excited to get my hands on. The team over at Nvidia has been kind enough to do a giveaway of 3 passes to the upcoming GTC conference, which is in the first week of October. If you'd like to enter, please check out the description of this podcast. You just need to share this interview on Twitter and tag me or Chai Time Data Science Show, or just retweet the one along with which this is released. This again has been a really insightful interview all about deep learning as a field and its evolution, broadly speaking, as well as Bryan's journey into the field. So I hope you enjoy it as much as I did. Without further ado, here's the conversation. Please enjoy the show. I'm honored to be interviewing the VP of Applied Research at Nvidia, Bryan Catanzaro. Bryan, thank you so much for joining me on the podcast.
Oh, it's my pleasure.
I have so many things I want to talk to you about. The 3000 series GPUs have launched. There's so much going on in research, but I want to start by talking about your journey. A little interesting fact I found about you. Did you know you're also on IMDb for a research-related movie?
You know, to be honest, I did not know that. I have done a lot of interviews and been filmed for various projects over the years, but it's very unusual for me to be credited somehow in a movie. And I guess maybe it was for that one documentary about the history of artificial intelligence, I guess, that I did. That was, that was a fun little project, but I had no idea that I had credits on IMDb. That's crazy.
It was for the Wired movie. You're correct.
Okay.
So that was for the audience to know about how much Bryan has been involved in the.
Well, don't expect me to be a Hollywood movie star. I am a researcher, so.
So, but talking about your journey, you've been involved for so many years in machine learning or deep learning, broadly speaking. You followed a traditional path. Were you always interested in what we call machine learning today? When did you find your interest?
I really started working on machine learning in 2006. And I was a new graduate student at the University of California, Berkeley, working on my PhD. And my path was a little bit unusual. So I had been working on tools for hardware design, actually, trying to figure out how we could make better computer chips. And I felt like this was important because I had interned 3 times at Intel in the early 2000s, and I had seen the difficulties that Intel was starting to run into because Dennard scaling and Moore's law were slowing down, and this was causing a lot of problems to sort of the traditional ways of building chips. And I thought, okay, well, we need to find better methodologies for building chips. So that's what I was thinking about when I joined Berkeley. And while I was there, I came to understand that it's likely that in the future there are there's still going to be some awesome chips that we could use to do amazing things, but the sort of way that we're going to go about unlocking the potential of all of this is through parallel programming. We're going to have like very, very parallel processors that have, thousands of cores. And then the question is, what kinds of workloads are we going to be able to run on those cores that are going to be important enough that they will justify the investment in parallel programming tools and frameworks and so forth. And so in 2006, I was involved in this project. We wrote a paper called the Berkeley View on parallel computing, and so I was involved in that, and that paper ended up being fairly influential. And as part of that, I was spending a lot of time thinking about applications of parallel computing, because I really felt like I needed to understand that before we could understand more about how the technology was going to develop. And it was obvious to me back then that machine learning was going to be the most important application for parallel computing. And so that's when I really started diving into machine learning and started taking graduate courses on machine learning at Berkeley, and really started learning more about what we could do with machine learning. And one of the funny ironies of all of that is that at that time, in the late 2000 decade, deep learning was out of fashion.
I had read that the culture in your campus was that the people were mostly skeptical if this would work effectively.
Yeah, I mean, I think it was the culture on pretty much every campus except for maybe University of Toronto, where Jeff Hinton was, or maybe New York University, where Jan LeCun was. Like deep learning was pretty countercultural. All of the big luminaries that I looked up to in the field were trying to do newer things, right? Because deep learning, like a lot of the ideas behind it are decades old, really. And Jan LeCun was publishing convolutional neural networks back in the 1980s, right? So it was like 30 years old, right? And so like it was hard for people to imagine that the future really was going to be dominated by deep learning. They thought, well, if that were to be the case, we would have seen deep learning succeed already, because it's been around for so long. And so people were really interested in graphical models, which are ways of capturing probability distributions and doing inference over probability distributions in kind of a mathematically elegant way. People were really excited about those, so I was working on those. And also support vector machines were really big, and so I spent some time working with support vector machines. And so so I was doing machine learning back then, but I didn't really start doing deep learning until after I graduated from Berkeley, and I started working at Nvidia. And that was it was interesting. I was in a research lab, so I had a lot of freedom to do what I felt was going to be useful. And my group was responsible for working on programming systems and applications for GPUs. So we're trying to figure out like how do we come up with important new ways of using GPUs that are going to be impactful for NVIDIA. And I had been working on machine learning on GPUs, and so I was paying attention. And that's when the ImageNet competition that Alex Krzyzewski won happened, was right after I had joined NVIDIA. And obviously that was kind of a watershed moment for the world. And everybody in the community was really kind of shocked by that. And so that's when I started working on deep learning a lot more intensively. I also met Andrew Ng at that time. So he had some students at Stanford that were working on some deep learning projects, and they wanted to be able to use GPUs in a better way. And so Andrew was looking for somebody at Nvidia to partner with, and Bill Daly, who runs Nvidia's research lab, said, well, Bryan is, our researcher that's doing the most with machine learning, so maybe you guys could meet up with him. And so I met up with Andrew Ng and his graduate students, including Adam Coates, who later became my boss. And we started working on some deep learning on GPUs, and all of that led to some pretty significant things. I guess CuDNN came out of that work, because I saw how much time people around the world were spending optimizing convolutions, and it was crazy. Like there were people at New York University who ordinarily would be working on like papers for ICML, but instead they were writing CUDA code because they needed their convolutions to go faster. And so I was looking at that and I was like, wow, there's a real need here for NVIDIA to step in and provide some libraries for deep learning, and that's when I built the prototype that became CuDNN. So that was important, and then I think we published this ICML paper in 2013 about how we can replace large amounts of traditional servers with a few servers with GPUs on it, and that was with the Stanford group.
The
And
year
that caught a
before
lot of
that, the trend
attention.
was more about HPCs, if I remember correctly, where Google was leading about how you could use a huge number of thousands of servers to get good results, I think.
Yeah. Google had this really strong bias towards MapReduce. And that's because at the time, Google had this belief that basically any computation could be done with MapReduce. And I mean, and which is probably true because, MapReduce is astonishingly powerful and flexible. But the problem is that it's very inefficient to do deep learning with MapReduce. And so we kind of showed like, hey guys, if you just use HPC style techniques and GPUs and, optimized software, you don't need MapReduce, and you can go from like 1,000 servers to like 3 and do the same work. And so that was, I feel like that was, an impactful paper. It's interesting because Google, I think, has obviously with the TPU and a lot of the other infrastructure that they've built, TensorFlow, for example, since that time, I feel like they have also kind of agreed that we need a lot more tightly coupled software and hardware to do deep learning, and so I think that's been good for the world. But I don't know, that's kind of my long-term story. I know that's kind of a little complicated. There's a lot of little pieces in there about, well, I did this and then it led to that and then it led to that, and so it's I mean, that's the truth of how I got to work in this field. And I wonder, what's the overarching message behind that? I guess the reason why I kind of went from one thing to the next as I was doing this work is that I was always thinking about what could I be doing that would be helpful to other people. Research, we're all driven by our own interests, right? Like
Yes.
research is an exploration, and it's we're driven by curiosity. We wake up in the morning, we want to know answers to questions, and there's so many questions. There's an infinite number of interesting and important research questions. And so the sort of principle that I have always operated on is, what out of all these questions, what's the question that I could work on answering today that would be most useful for other people? And I think that has allowed me to kind of be responsive to the way that technology has evolved and the way that algorithms in the community has evolved, and that's kind of helped my research, I think, ultimately connect with things. And I don't know, that seems maybe a little high level and a little vague, but if I had to choose like one thing that kind of underpinned that journey, that would be it.
Okay. That's I think where the cutting edge in research also really lies. You really need to think about the broader picture. Maybe also try to peek into the future and see what would be more effective. But
Yeah.
Going back in time, I also read you were working on problems involving CPU optimization. How were you writing code back then? Were neural nets even in existence? There was no CuDNN, of course.
Um, CPU code for deep learning
Yes,
specifically,
yes.
or
Sorry.
okay, yeah. Um, well, back then, the way that you wrote efficient CPU code was you wrote it with threads. It could be P threads or it could be OpenMP threads. Those were the two like threading models, and then you would use SIMD intrinsics. So, Intel CPUs have this whole family of vector instructions that started with MMX with the Pentium back in the 90s. And then, every few years they sort of increased the scope of those instruction sets. And um, they those vector instructions on the CPU can be pretty powerful. However, they're difficult to use when you're programming in kind of a traditional way, like using C++. Just writing traditional code, you're probably not going to be using those instructions. Really, sometimes the compiler will do it for you, but it's kind of risky, and most of the time it doesn't work. So, or at least back then that was the case. And so what we would do instead was actually write uh, code where we were explicitly instantiating those vector instructions in order to try to use those vector units. And that was a lot of work. I remember when CUDA first came out, it was November of 2006 when the first beta version of CUDA came out. And I looked at the code for a CUDA program and I thought, wow, this is so much easier to write than pthreads plus vector intrinsics, but it does kind of the same thing, right? Because the GPU architecture is also very vectorized. The difference is that the vectorization in GPU code is done implicitly because the processor has a lot of extra support to help with making sure your program is correct. The reason why compilers have a difficult time using vector instructions on the CPU is that there's a lot of corner cases in your code that make it unsafe to use those vector instructions.
Hmm.
If you try to do that, you'll actually compute the wrong thing. And so with the GPU, the vectorization happens automatically because the hardware and the software are able to put in all of the sort of guards and safety mechanisms that are necessary to make sure that your code is correct when it's running in a vectorized way, except that if it needs to not be vectorized for correctness, then it will automatically kind of serialize the execution so that you can get the right answer.
I,
So I when I saw that in 2006, I thought, okay, this is the future of parallel computing for me. I'm going to stop worrying about threads. I'm going to stop worrying about vector intrinsics. I'm just going to write CUDA code, and that made my life a lot easier.
I sort of just wanted to point out how even in just a few years things have changed so much. People today probably just think CUDA is a software you need to download to be able to use PyTorch or TensorFlow effectively, and
That's
people back
right.
in the day were also using it pretty effectively.
Yeah, that's right. It's very interesting that CUDA has become so widespread, and it's kind of the foundation of so much work that people do around the world. We don't even really need to think about it very often, and I think that's a testament to the success of the framework. That it's been able to become so reliable and so there's been so much investment in building libraries that use it that it's not even an issue anymore. People can just get their work done, which is obviously what we all want to do.
Definitely. So coming to today, you're the VP of Applied Research at Nvidia. What does a day in your life, let's say on non-pandemic days, what does a day in your life look like? What tasks are you involved in?
So my team is about 40 researchers, and we work in four different areas: in graphics and computer vision, in audio, primarily speech, in natural language processing, and in applying machine learning to systems problems. as NVIDIA is a systems company, we have a lot of interesting systems problems. So those are the four areas that we work in. And my job is to kind of support all of that work that happens in all of those areas. So how do I do that? I do a lot of learning. With that amount of research that's going on, there's always a lot of new ideas to think about and to connect, to make sure that the research is proceeding as we would expect it to, and that people aren't being blocked. They haven't run into obstacles that prevent progress, and make sure that people have the right resources, make sure that people are talking to each other appropriately, because often it's the case that there's multiple people working on related things, but they may not know that all of the things that are going on are related, because it's at the size of 40 people, it's not possible for every person in the team to know what every other person is doing, right? Because it's too much that's going on. So my role is really a supportive role, that I'm trying to help enable the researchers on my team to do their very best work. And I do that by learning about what they're doing, and by listening, and then by thinking about what are the problems that they're facing, and how can we overcome them, how can we connect them to resources that will help them succeed. And honestly, we do a lot of brainstorming together, because research is frustrating isn't quite the word that I want to use, but if research has to be risky. If you're doing research and there's no risk to it, then it's not research anymore. It's a development activity, which is important, right? There's lots of development work that needs to be done in the world, but as far as for the work that my team does, it is going to always have that element of risk, which means every project is always on the brink of failure, and every project has moments in it where we think, well, maybe this is it. Like maybe this research is just a bad idea. And at that point, we do a lot of brainstorming to try to figure out what's happening. Sometimes we can brainstorm new experiments to run that help us kind of unstick ourselves in the research. Sometimes we discover that actually the research was a bad idea, but then we kind of brainstorm the things that we've learned from it, so that we can brainstorm new projects to do. So I do a lot of that as well, a lot of coordination. I also do a lot of recruiting. I've built this team. My team is now 4 years old. We just had our 4-year anniversary last week, actually.
Awesome.
And
Congratulations.
thank you. So when I started this team 4 years ago, it was just me. And so when I think about the progress that we've made over the past 4 years, and all of the great people that are doing such amazing work, it brings me a lot of joy, and so that's been my job, is to build that team and build that group and make sure that we succeed at our mission of transforming NVIDIA by using AI to do new things the company hasn't been able to do before.
Could you help us understand, NVIDIA is a company that sells GPUs to many people, it looks like that. Why is research so important to NVIDIA? Where does it come in the ecosystem?
Yeah, well, NVIDIA is a technology company, and technology moves quickly. And there's always this problem in technology that if you are too focused on building the thing that you know how to build, that is sort of in your comfort zone, then you lose that innovative edge that takes you to where the market is going to be. And then ultimately undermines your position in the technology industry. Technology industry changes so fast. And so it's really, really important for research in a company like NVIDIA to raise the headlights. That's one of the things we talk about, of like, if you're driving down a dark road at night, it's helpful to have the headlights be shining brighter and higher up, so that you can see just a little bit farther into the future. And research at NVIDIA has had a tremendous impact on the company. We talked about CuDNN. I think CuDNN has been a very valuable project for NVIDIA. It's been one of the primary ways that NVIDIA has established GPUs as the best place to do artificial intelligence research because this library exists. And, many other companies could have made CuDNN. Many other companies could have made processors for AI. Why is it that NVIDIA has been so far ahead of its competition? I think, well, we did the research. We were willing to ask those questions. What might be changing about the future? How can we build prototypes of things that might have a big impact, and then, invest in those things early on. NVIDIA invested in deep learning far before other companies did. Other companies made lip service about how AI is important or machine intelligence is important, but I remember when Jensen Huang gave his keynote at GTC 2014. Everybody in the audience was completely surprised and, to be honest, a little bit frustrated that he would spend the entire keynote on artificial intelligence and deep learning. And because they didn't want that. People wanted to come to his keynote and hear about more traditional high performance computing applications. They wanted, they wanted more of the same. And Jensen gave them something different that they didn't want. Jensen always likes to talk about $0 billion markets, where NVIDIA likes $0 billion markets because that means we're at the beginning, right? And so I think that's a crucial job that research has, is to help the company find those $0 billion markets that are going to end up changing the world. CuDNN is one example, and an AI that I happen to be involved with, although many other people were involved with that as well. But I think it's undeniable that the research that we did really helped the company jump into the future quicker than its competitors. But there's been others. Our work with ray tracing it's really inspiring to me, actually. When I was an intern at NVIDIA in 2008, back then NVIDIA research was about 10 people. It was very small. And it was new. NVIDIA didn't really have a research organization before about 2007. So this was all brand new. And most of the people working in NVIDIA research at that time were working on ray tracing. In fact, I remember one day we had our NVIDIA research team meeting, and there was, like 8 people there in the office in Santa Clara, and then there was a few people, calling in over the phone from other places. Jensen walked into the room and just sat down. He just wanted to listen. He just wanted to hear what research was happening about ray tracing in 2008. He sat down. He didn't say a word. He just listened. And then at the end of the meeting, he left and went on to do his other stuff. And, that was just incredible to me for a number of reasons. I mean, obviously Jensen's an important guy and he has a lot of demands on his time. For him to physically take time out of his day to listen to the research that people were doing, I thought, it was a very unusual experience. And it showed that he was paying attention and he was trying to understand, what this new research lab was doing. But then the other thing I wanted to point out is that the ray tracing research that was happening back then ultimately led to some pretty significant results. With the launch of Turing in 2018 that has ray tracing hardware and software that allows us to do real-time ray tracing for video games and design applications. All of that work builds directly on the research that was happening 10 years before. So it took the company 10 years to go from a small research team to a technology that we shipped that changed the world. I don't know many other companies that would stick with something for that long, right? It takes a lot of focus and a lot of sort of an inner compass, sort of a belief about what the future is and where the future is going, to be able to continuously improve and develop a technology like ray tracing to that degree. And NVIDIA has done that several times in several different ways. And so I feel like it's one of the reasons why I like working at NVIDIA, is that I feel like we have both the need at NVIDIA for people to be working on stuff that is kind of points the way to the future because we work in the technology industry, and so every technology company needs that. But we also have the opportunity in the sense that we have a company who is built to focus on things over the long term, to work on significant projects that maybe the rest of the world doesn't understand yet. Like CUDA, if you look at NVIDIA's stock price between 2006 when CUDA was released and 2016, there was basically a 10-year period where NVIDIA, all of that work that NVIDIA was doing, laying the foundations for machine learning and parallel computing that we see today, was not being valued by the rest of the world. Like the rest of the world thought, why are you wasting your time, NVIDIA, on CUDA? You're a gaming company. Just make us faster gaming chips. That's what we really want. And, so the company is able to make those investments long term because it has this strong vision about what we think is right, our vision of the future of technology. And so, and of course, that vision is informed by the research that we do. And so I feel like there's this really great combination of like need for research at NVIDIA and also the opportunity for research to actually connect to things that matter. And that's, I think, pretty rare.
As an average gamer, ray tracing is sort of frustrating because now I get to watch myself lose with very nice shadows.
Yeah.
So it's not so good for average gamers, maybe.
Well, we're going to continue pushing on ray tracing. We're going to keep making it better, and games, there's just more and more games that are using it, and more design applications that are using it. And Jensen yesterday at the launch of the RTX 3000 series was talking about how 20 years from now, we're going to be in these incredible virtual environments where, instead of transporting ourselves physically, we're going to transport photons at the speed of light that allow us to collaborate and communicate all around the world. And it's going to feel almost as if we were there. And we're going to, look back at this time and realize that that's when all of this started. So, we have done a lot over the past 10 years with ray tracing, but I think, where we're going to go from here, it's very exciting.
Definitely. And in one of the previous talks by you, I was actually reading or listening that in maybe your 2013 work actually led to the CEO completely changing the vision of the company to more towards deep learning facing, just because they were so interested by the results that were shown. I might be wrong in my study though.
Yeah, I mean, it definitely did have a big impact. After we published that paper, I started meeting with a lot of senior management at NVIDIA who wanted to kind of understand more about deep learning, and they wanted to understand more about the computational dimensions of deep learning. I think also about that time, NVIDIA started getting a lot more orders for GPUs from unusual customers, right? Like before around that time, before we published that paper saying, hey, GPUs are awesome for deep learning, a lot of NVIDIA's compute customers for GPUs were coming from traditional industries like maybe the oil and gas industry, or maybe the traditional supercomputer industry. And all of a sudden, NVIDIA started getting these orders from companies that were more like internet focused, and companies that were starting to use deep learning to try to improve their products. That mostly started with internet companies. And so I feel like NVIDIA's management was watching that and thinking, well, that's unusual. Why would we start getting new orders from unusual places? And then they kind of put the dots together and realized, okay, the technology is changing. We have the ingredients to do great things that will change the world. And in some ways, NVIDIA had been looking for that for a long time, right? Like I said, CUDA was released in 2006, so this was like in 2013 time period where all of a sudden there was this new opportunity and to really make GPUs awesome for machine learning, and that was management had been waiting for that, right? Like everybody around the company, we knew that CUDA was important. We knew parallel programming was important. We knew that GPUs were important. And there was all these different things that people were doing with them, but it wasn't clear, what if all of those things was going to lead to, meaningful product growth for Nvidia and sort of have that kind of impact, the really broad, large scale impact that we were hoping to have. And so everyone was looking for that and was really prepared. And then when deep learning came along, the company jumped on it instantly and started, really investing in it. And I think that that was only possible because of the vision that the company has. Again, there's a lot of resistance, as there always is. Whenever there's something new that is requiring a lot of attention, there's going to be people who say, well, this isn't actually that useful. It's not actually that new. It's not actually that important. And, NVIDIA was able to kind of ignore a lot of that and just push ahead and do what it thought was right, because the company really is driven by our vision and by our belief about how the future is going to work. We're willing to make big bets, and we're willing to, do hard things if we feel like there's a good chance that that's going to lead to significant impact. Then we're willing to make big bets, bet the whole company on something, and it's either going to turn out really great or it's going to turn out terrible. But we would rather make that bet than sort of move along with a kind of timid portfolio strategy where, it's not really quite clear exactly what the priorities are. And then, none of them actually get funded or invested properly, which then kind of leads to suboptimal outcomes. So I feel like that's a great strength that NVIDIA has. And like we've been talking about, research is kind of a key part of the way that NVIDIA executes on that mission.
I really wanted to dive into that tangent because just to showcase that it's really a visionary, NVIDIA is really a visionary company, and all the groups are sort of really looking towards the future and willing to make the big bets, like you had mentioned.
Yeah.
Throughout these years, I'm sure you witnessed, if I may, machine learning trends. What has been your favorite change or trend in ML research throughout these years?
My favorite trend, I would say, is the move towards pre-training and fine-tuning. I think it's such a powerful way to think about solving machine learning problems. And we see it in so many different fields these days where we have pre-trained models. They may even be trained in an unsupervised way. And then we fine-tune those models with a small amount of data to solve concrete problems. I think that's just such a powerful way of taking advantage of large amounts of data and large amounts of compute in a way that can scale to many, many applications.
They're definitely two different problems, if I may, to hardware. With one which is maybe which requires a lot of compute. The other one, like you mentioned, is the new trend, which is fine tuning and using pre-trained models. What do you think? Do you have any overview of both sides? Because I know NVIDIA contributes to both. To quote, the Megatron from last year was one of the biggest transformer models that was trained.
Yeah, that's right. And Megatron, it's a project that my team built, so I'm very proud of it. And, I expect we're going to be doing some awesome things in the future with it as well, training the world's largest transformers. I think we need both, right? So it's definitely true that deep learning requires scale to get the best results. We need the biggest data sets and we need the biggest models. And that means we need the biggest computers. And so it's definitely true that we have a lot of work to do in in scaling up deep learning. And obviously NVIDIA is involved in that. However, we also have a lot of work to do to figure out how to use machine learning and also new ideas that kind of change the way we think about what deep learning is and what it can do. And many of those things are best done at a smaller scale. And individual researchers with, relatively modest amounts of computing access.
Maybe a 3090 today, because that's sort of more affordable now.
Oh yeah, 3090 is, I'm not sure if that's really even that small. It's a pretty big GPU, as Jensen called it yesterday, the BF GPU. 24 gigabytes of memory is a lot of memory. You can do a lot with that. Um, yeah, yeah, so what can you do with one 3090? You can do an awful lot with one 3090. And there's also a lot of like I was saying, sort of mindset shifts, like different ways of thinking about what deep learning is. And, have we learned all that there is to learn about deep learning and how it should be built and how it should be used? Absolutely not. I'm very inspired by research that points out, new ways of thinking about deep learning. And I think we've got a lot more of that kind of research left to discover.
What do you think would be some maybe underrated areas of research today in 2020?
Well, one of the things that I really like is like different kinds of deep learning models. Um, I'm a big believer in invertible flow-based models. I don't know if you have seen the paper from Laurent Din in
I haven't, sorry.
2014 on, yeah, nonlinear independent components estimation. The NICE is the acronym for it. That paper, I think, really kicked off a lot of work on invertible flows, and um, we see that work having more and more applications. So one of the things we've been doing in my group is we figured out how to use a flow-based model for speech synthesis. And the flow-based model actually had a number of advantages. It was faster to deploy, so it was more efficient, and it sounded really great. And it was also easier to train than a traditional neural network. And these flow-based models, they work in a very unusual way. So what they're trying to do is to learn a probability distribution, but because we don't know the form of the probability distribution, what they do is they transform an unknown probability distribution into a Gaussian distribution, which of course we have a closed form for. But they do it critically in an invertible fashion, step by step, going from some distribution we don't know to a Gaussian. And because it's invertible, then that allows us to run the model inside out. And so when we train the model, we're just trying to take data and turn it into Gaussians. But when we use the model, we take Gaussians and invert them back into this unknown distribution that is too complicated for us to reason about. For example, the distribution of pictures of faces or the distribution of samples of audio. We don't know actually how to describe the distribution of audio samples. We know how to describe the distribution of Gaussians because it's really, really easy. And so that insight that we can actually do both if we have an invertible model, and here's how we can build invertible models. I feel like that work is really interesting and really underrated. We hear a lot about GANs,
Yes.
and I love GANs. These invertible models can solve similar problems to GANs. In fact, I would say, have a little bit more principled mathematical underpinning behind them than GANs do. And I believe they have some advantages over GANs. They're easier to train, and because they don't have this min-max optimization problem that can sometimes lead to mode collapse where the GAN actually doesn't learn anything. So the flow-based models, I think, have some advantages. They have some disadvantages as well. I think one of their big disadvantages is that because the model has to be invertible, it has to be able to go both directions. The parameters end up kind of having to do double duty. So these flow-based models tend to need more parameters because I think the power of each parameter is kind of being used in sort of this more diluted way, and so they can have some difficulties, I guess, with deployment speed and so forth because the models can be bigger. But sometimes they can actually be great. Like our speech synthesis flow-based models, they work great, and they're very efficient. So I wish that the world could spend more effort looking into flow-based models. I feel like often the thing that gets the best results in machine learning is the thing that gets the most attention, the most polish, the most investment, not necessarily the thing that is the easiest to use or the best in some, abstract sense. And so I feel like GANs have been, invested in really heavily. There's some alternate universe in which flow-based models got the same amount of investment as GANs. They might actually be like really super amazing. So I really love that kind of work.
It's actually I would say there's a Kaggle competition running based on detecting audio, and Kaggle is pretty good at finding pretty much all of the research papers. I haven't seen any discussion about flow-based models, so I think it's really underrated. Maybe.
Yeah, maybe, who knows? Like maybe it's because they are harder to use for some people for some applications. But we've really enjoyed working with them for our speech work, and I've also seen a really great paper on using flow-based models for neural importance sampling for ray tracing, actually. Because when you're doing ray tracing, you have this problem that you have to figure out where to send the rays. If you send the rays in a uniform pattern, you're going to waste a lot of them because the scene complexity is not uniform. And so there's this really great paper on using invertible flow models for neural importance sampling, and I felt like that was really awesome work.
Now, going back to the research question, as an effort in this podcast, I try to understand how great researchers work. Could you maybe give a very broad overview of what a research pipeline for maybe one of your group looks like? How do they pick the problems? How do they approach them?
Yeah. So our group is an applied group. Applied research to me means that we focus on application. Some research is focused on theory. There's some work that's, advanced development work that is required to take prototypes and turn them into products. We try to keep kind of in the middle of that spectrum. We try not to get too theoretical. We also try not to do too much development. We try to focus on building prototypes of new things that people haven't been able to do before that hopefully matter to NVIDIA. So I usually think about organizing our work into 4 different categories. The first is the neural network itself. And this is the one that gets a lot of attention because you can publish it in NeurIPS. And all of us love publishing. So we do that. We do work on new kinds of neural networks. However, I would say that work is kind of overrated in the sense that it gets more attention really than it deserves. And I think that's just a function of kind of the academic publishing market. The other 3 things that we do are just as important. So one of them is application framing. So if you're doing applied research, you're trying to build a prototype, you need to think about, what is my machine learning doing? What are the inputs? What are the outputs? What are the guardrails that get placed around that machine learning? Because every model fails, right? So every machine learning model is going to have weaknesses. Can we make it so that when it fails, it doesn't destroy the goodness of the application we're trying to build? There's a lot of thinking that goes into actually using machine learning in an application, and we call that application framing. It's really, really important. There's been a lot of cases in our research where the exact same neural net fails to solve a problem, and then we change the problem that we ask it to solve, and it succeeds. And the changes that we made in the application framing from a mathematical point of view shouldn't matter to the neural net, but there's always these tricks about whether or not the optimization process can actually succeed, and whether you can learn something that generalizes well. You can dramatically improve the generalization of your neural net by using it in a smarter way. And so that application framing work is very important. The third thing that we do a lot of is data set work. For any application of deep learning, the data set is really a critical part of the algorithm itself. We do not take the excuse that somebody else is responsible for making data for us for our research, because the data is so key to the application. we have to own that as much as we can. It's, in my mind, just as fundamental to the overall algorithm as the structure of the neural net itself. And if you think about how machine learning works, we're changing the weights in the algorithm based on the data. So the data becomes embedded in the overall algorithm that we're creating. And so it's very, very essential. Oftentimes, data set work involves not just cleaning the data to make sure there's no mistakes in it, because if you train a model on garbage data, you get a garbage model. But it also involves creating pipelines that can create new data. So how can we create an engine that's going to continuously provide more and higher quality data for this application? And then the fourth area that we work a lot in is systems. So both systems for deployment as well as systems for training. We need to be able to deploy and to train the largest possible models, which means that we have to be very thoughtful about how we use computing systems. And so I would say all four of those areas are really important. So that's kind of a sort of an organizational thought about like what kinds of work that we do. I think to your question about like how do we go about choosing projects, I always am balancing three different things. So we're balancing interest of the researcher. It's essential that every researcher loves the project that they're doing, because research is about passion and about creativity. And if you don't love the research that you're doing, it's going to be bad research. You're not going to come up with good ideas if you don't love the work you're doing. It's just very fundamental. So we need to have projects that are exciting to the people doing the work. The second thing we're balancing is interest to the company. So I care deeply about making sure the work that we do matters to Nvidia. This is how I ensure that the company understands the value that we're providing. I like getting paid. I like working at a company that, understands the reason why we're doing the work that we're doing. If we just started doing stuff that didn't matter to the company, after a while, the company would ask us, why are we making this investment? And so we care deeply about working on things that connect with the priorities and the strategies and the sort of vision of the company. So that's the second thing. And then the third thing that we always have to pay attention to is feasibility. Artificial general intelligence would hit those first two categories really well. Like there's many researchers who would absolutely love to work on artificial general intelligence. They would wake up every morning very excited to work on that. Nvidia would love it if we created artificial general intelligence. Clearly, if we did so, that would be a very valuable invention, and it could help Nvidia make a large amount of money and have a lot of impact on the world. And so clearly, artificial general intelligence would be great for the company's strategy. But as far as feasibility goes, personally, I don't think that it's feasible in the near term, and so I think we should not be working on it. Like we're an applied research group, we need to be working on applications, things that are 1 to 2 years out in the future. And so we don't work on artificial general intelligence because I don't think that would be appropriate for sort of our particular mission. So so those are kind of the three things that we're balancing. For individual researchers in the team, we try to give them freedom to look around. We also try to give them context. Sometimes the company needs things. Sometimes we get requests from the rest of the company. Could you look into this? We really need some help with this. So we'll do that if we can find somebody who's interested in doing that. Sometimes researchers propose things that I haven't really even been thinking about, but we recognize this is a good idea and we do it. So it's kind of a balance of all those things. But I guess one of the reasons that I wanted to tell you about those 4 different categories of work that we do is that, I'm always telling the team to think about the work that they choose to do outside of things that, that look like algorithmic innovations that we could publish at NeurIPS. Because I feel like if we only did that, we would significantly underperform sort of our promise and our mission. we really need to focus on those other three areas as well. So that's kind of the framework that we use to think about these problems.
It also sounds like a very natural framework. Looking from the outside, less organizational, much more natural, if I may.
Yeah, I mean, NVIDIA generally tries to make decisions based on what is true rather than sort of organizational constraints. I think it's one of the benefits of working at a founder-run company. Like really, NVIDIA is one team. It's Jensen's team. He founded the company. He's the CEO. Everything that we do contributes to one mission and one team. And so, we don't tend to make decisions about what we work on based on kind of organizational boundaries or sort of bureaucratic processes because we try to always remember that at the end of the day, there is just one team. And so all of us are working on the same project, which is to, help this organization change the world.
You had also mentioned systems, which allows me to segue into the very exciting event that happened yesterday. I've been up since yesterday night. It was nighttime in India. The 3000 series. Have you tried that in your research groups? Do you have an overview? Because I know the benchmarks are yet to come out. If you could maybe give a teaser.
Yeah, well, we're very excited about the 3000 series GPUs. I think it seems like the internet was happy about them yesterday. I have also spent a lot of time looking at what people on the internet are saying about them because
there were two groups. One that was crying about the recent 2080 Ti purchases, and the other which was really happy about the 3090.
Well, right. It is always the case that when you release a product that's just better in every way than the old version of the product, that it does make some obsolescence happen. I don't really have much to say about that other than I'm really excited about the new stuff. Ampere GPUs, I think, bring a really great combination of raw performance as well as targeted acceleration for the things that really matter, like ray tracing and artificial intelligence. And I think people are going to really enjoy gaming with Ampere GPUs. I think they're going to really enjoy training neural networks with them. Overall, I think it's just a really great product.
Do you think the 3090 would also impact a lot of indie researchers who were maybe not able to earlier approach bigger problems, if I may?
Yeah, I mean, that's kind of always been the purpose of the Titan GPUs. Jensen has pointed that out many times, that there's this need for individual researchers that they do want to do some larger scale things, but they're maybe not a large company that has access to like a whole data center full of GPUs. What can we do to help individual researchers? And the Titan GPUs have always been about that. They've always been like a really great way to do individual research. And the 3090, when Jensen announced it, he connected it directly with the Titan, right? He said, okay, the Titan RTX, it cost $2,500. Now we have the 3090 and it's only $1,500, but it's much faster and much better in all these ways. And so so definitely I think the 3090 is aimed at individuals who are trying to push scale just a little bit and do some exciting things, but obviously not ready to go or not really in the right not really accessing those very large data centers. So the 3090 I think is going to be great for deep learning hobbyists and researchers for sure.
Absolutely. I've been really debating if I should cut down my chai expenses to invest into one. So I've been so excited. I really don't love my 2080 Ti anymore.
Oh, well, that case looks beautiful. It looks like your case is probably big enough that it could fit a 3090. Those 3090s are pretty big. So
I hope so. So this is a repeat question on the podcast, but one of the final technical questions for you, if I may call it technical. How do you suggest someone with a non-traditional background to get their break into the field of machine learning or deep learning?
Well, I would say that having a non-traditional background is not a barrier or not an insurmountable barrier. I think, we've definitely hired some people over the years who come from non-traditional backgrounds. I think the thing that kind of allows all of them to succeed is just an intense sense of curiosity. People that are just enormously curious can learn very quickly. And also coupled with that intense curiosity is what I would call iteration speed. So, I kind of think about stochastic gradient descent as a algorithm for life. That the way stochastic gradient descent works is that you try to pick a direction as best you can, even though it's very noisy. You're not sure exactly what the right direction is to go towards the optimum, but you just pick a sort of good direction and then you take a step in that direction and then you reevaluate and you ask yourself, can I improve that direction just a little bit? And then you take another step and then you take millions of steps, right? So it's very iterative. And stochastic gradient descent really requires that. Like, of course, we would love to have optimization algorithms that just took us to the optimum directly. Who wouldn't want that? Instead of taking a million steps, let's just take one. The problem is that we don't know how to find that direction to go exactly to the optimal. We don't know where the optimum is. And so stochastic gradient descent is the way that we find optima in deep learning. And I think it applies to life as well, that like the most important thing is take a lot of iterations and always be reevaluating, your progress and sort of trying to update your direction just a little bit. Not trying to like radically change the direction, but just try to, based on the information you have, the noisy estimates that you have of where the steepest gradient is, just take a step, in that direction and then take another step and, take a million steps. And so I feel like the people that succeed that have non-traditional backgrounds are people that they are just iterating so quickly. They are taking millions of steps to learn and to grow. And they don't let perfectionism get in the way. They just start doing stuff. And the stuff maybe not be the best stuff the world's ever seen, but it doesn't matter because they just learn so fast. So that's kind of how I think people succeed.
I know we're almost out of time, but if I may, can I squeeze in a rapid fire round where I have a few 4 or 5 questions lined up for you?
Okay.
Favorite game of all time, if you have one?
I think it would be Final Fantasy VI.
Okay. Not the 7?
I like 7 as well, but 6 was more important to my childhood, I guess. 7 didn't come out until I was in college, and so it was really important to me. But I kind of fell in love with 6.
Okay. Favorite game with DLSS?
Death Stranding.
Okay. Favorite GPU today?
Well, it would have to be the RTX 3080.
Okay. Favorite framework, TensorFlow or PyTorch?
Oh, PyTorch. My team is exclusively PyTorch. Every once in a while, somebody starts a project in TensorFlow, but we convert it to PyTorch as soon as we can.
Finally, in my research about finding out details about you, I learned that you're also a great chef. Can you share your favorite dish or maybe a dessert that you baked recently?
Well, I bake a lot of bread. And recently I've been obsessed with the tartine morning roll. And it is built out of a croissant dough that has a lot of orange peel and cinnamon and sugar mixed in with the croissant dough, which of course has a lot of butter. So it's very indulgent. It's really amazing, and I've been enjoying them a lot.
It looks like really amazing things come out of ovens at Nvidia.
That's right, man. I love it every time Jensen takes something out of the oven. It brings me so much joy. I don't know if you saw yesterday on the RTX 3000 series reveal that Jensen had hid a GPU behind his spatulas.
I did.
And then he pulled the GPU out from behind the spatulas. That was the best. because everybody's always been talking about Jensen's collection of spatulas. They're kind of iconic at this point. And so for him to like have a GPU like hiding behind the spatulas for the whole time and then just pull it out, I thought it was awesome.
Okay. Bryan, thank you so much for your time. But before we end the call, what would be the best platform for the audience to connect with you?
Twitter. So I like my Twitter account the best. It's just my last name with all the vowels removed. So CTNZR.
Okay, awesome. Thank you so much for your time and for sharing your journey and this amazing overview of your research work.
Well, it's been a pleasure. Thank you, Sanyam.
Thank you so much for listening to this episode. If you enjoyed the show, please be sure to give it a review or feel free to shoot me a message. You can find all of the social media links in the description. If you like the show, please subscribe and tune in each week to Chai Time Data Science.